Yes, yes, yeah, you can start.
Yeah, welcome to APRG seminar this week, and it's my pleasure to introduce the speaker today, Dr. Naik from Harish-Chandra Research Institute, Allahabad. So he will talk about mean value property in limit for eigenfunctions of his Laplace Beltrami operator and symmetric space.
Bingo is my voice is audible. Yes. So, good afternoon. I would like to thank the mathematics department. Actually, there was so much noise therefore.
Other people online audience go near,
or you can take that. That's better. Right?
Okay.
Yeah.
Maybe we can just ask someone in the online audience.
Can you ask somebody? Yeah. So that they can hear me.
Yeah.
Yeah.
Can you hear us, sir?
Hear me?
I could hear offline. I could hear Muna when he talks.
Okay.
Okay. Yeah. Then you be there.
Yeah. I cannot see here actually. I can stand here. Right? Sorry. Good afternoon. I would like to thank the mathematics department for giving me an invitation to present a talk here. My special thanks goes to 4 persons, namely Professor S. Thangavelu, Professor E.K. Narayan, and Professor A.K. Nandakumaran and Apurva Khare for some special reasons. The title of my talk is Mean Value Property in Limit for Eigenfunctions of the Laplace Beltrami operator on symmetric spaces. I will begin with certain notations. The symbol F1 comparable to F2 for two positive expressions F1 and F2 means that there are constants C1 greater than 0 and C2 greater than 0, so that C1 F1 less than equal to F2 less than equal to C2 F1. For x belongs to Rn and a function f on Rn, let Lxf denote the left translation of f defined by Lxfy is equal to f of x plus y. Here y belongs to Rn. Let Bx, R denotes the ball of radius r with center at x belongs to Rn. Let X, R denotes the sphere of radius r with center at x belongs to Rn. Let B be the measure of B0, R and alpha n be the measure of Sn minus 1. This volume in value operator BRF is given by BRFA is simply average of f over ball of radius r with center at x. So one can express this BRFX as f convolution MRX, where MRY is the indicator function of B0, R divided by its measure. Similarly, I define spherical mean value operator MRF is given by MRFX. MRFX is simply average of f over sphere of radius r with center at x. This precisely MRFX is equal to 1 by measure of SS, R into integration over Sx, R Fy d omega Ry. Here d omega r is the surface measure of S, R. FX, if you simplify that, you will get this is equal to 1 by alpha n integration over Sn minus 1 f of x plus r w d sigma w. Here d sigma is the surface measure of Sn minus 1. Radial part of a function f on Rn is given by Rfx is equal to 1 by alpha n integration over Sn minus 1 f of norm x w d sigma w. Precisely Rf is the average of f over sphere of radius norm x with center at 0. This Rf is a radial function, and this we will call this R as radialization operator. Look at the expression of MRFX. This Rfx is nothing but m norm x f0. To look at this RLyFX, this is equal to 1 by alpha integration over Sn minus 1 LYF norm x w d sigma w. Simply write down the definition of LYF, then you will get this is equal to 1 by alpha n integration over Sn minus 1 f of y norm x w d sigma w. This is equal to m norm of x fy. Look at the expression of MRFX. Remember this expression, we will use this thing later. So RLyFX is really m norm x fy. Delta is equal to summation I is equal to 1 to 1 del square by del I square with the Laplacian on Rn. a twice continuously differentiable function on Rn is called harmonic if and only Laplacian of f is equal to 0. So it is known that a continuous function f on Rn is harmonic if and only if this Brfx is equal to fx for all x belongs to Rn and for all r greater than 0. That is to say that a continuous function f on Rn is harmonic if and only if f satisfies mean value property with respect to the ball averages. This is called volume mean value property. Similarly, there is a spherical mean value property. We say that is a harmonic if and only this MRFX is equal to fx for all x belongs to Rn and for all r greater than 0. We simply say that f is harmonic if and only f satisfies mean value property with respect to sphere average. Since I can express this spherical mean value operator in terms of radialization and left translation operator, one can really rephrase this spherical mean value property in a different way. That a function f on Rn is harmonic if and only r Lx fy is equal to fx for all x belongs to Rn and for all y belongs to Rn. Now one would like to ask an asymptotic mean value property for harmonic function. What does that mean? One would like to ask this following question. Let f be a continuous function on Rn, so that limit r tends to infinity Brf is equal to f. Will it imply that f is harmonic? If f is harmonic, then Brf is equal to f. Therefore, limit r tends to infinity Brf is equal to f. But we are asking the converse. We are asking this question that f be a continuous function on Rn, so that limit r tends to infinity Brf is equal to f. Will it imply that f is harmonic? The answer is yes, if you assume uniform convergence on compact sets. Okay, and to the best of our knowledge, the earliest result of this kind was due to Plancherel and Polya in 1931, but his result is only for R2. A more recent result is due to Benjamin and Waite and in 1989, and his result is for Rn. So precisely, result is like this. If for a continuous function f on Rn, limit r tends to infinity, Brfx is equal to fx uniformly on compact sets, then f is a harmonic function. I have taken the ball average to pose my question, and I have written the theorem in terms of ball average. Similarly, you can ask the question for sphere average, and analogous result holds true for sphere average as well. Now, this question makes sense for any general Riemannian manifold. In any general Riemannian manifold, we can talk about geodesic sphere and
Sphere average is concerned, then ball average is also
other way.
oh, the other way.
Yeah. So the thing is, okay, this question makes sense for any general Riemannian manifold. We can talk about geodesic sphere and geodesic ball. To any Riemannian manifold, we can associate a measure which we call Riemannian measure. Thus, we can integrate a function on a Riemannian manifold. So we can talk about volume of a geodesic ball. And in any Riemannian manifold, there is an analog of Laplacian, which we call Laplace Beltrami operator. So this question makes sense for any general Riemannian manifold. So what we have done, we have proved that this result is true for any rank 1 symmetric space of non-compact type, and more generally for diametric spaces. This rank 1 symmetric space of non-compact type or diametric spaces, they are Riemannian manifolds. So I am stating the simplest form of our result, which we have proved. So this is our result. Let X be a rank 1 symmetric space of non-compact type, and f be a continuous function on X if limit r tends to infinity Brfx is equal to fx uniformly on compact sets, then f is harmonic. Okay, here actually I am using the notation of which I developed for Euclidean space for Riemannian manifold as well. So here delta is the Laplace Beltrami operator. So it's precisely said that if ball average of a function converges to the function uniformly on compact sets as the radius r tends to infinity, then f is harmonic. Harmonic functions are really eigenfunctions of Laplace Beltrami operator with eigenvalue 0. For all other eigenfunction of Laplace Beltrami operator, there is an analogous mean value property, which we call generalized mean value property. So in view of generalized mean value property, it makes sense to this result for all other eigenfunctions of Laplace Beltrami operator, but But to state that result, we need some preliminaries about symmetric space, which I will do. I hope you are, I hope the motivation and starting point of our work is really clear to all of you. So let me quickly go through some preliminaries about symmetric space. Symmetric space, let G be a connected non-compact semi-simple group with finite center and of real rank 1, and K be a maximal compact subgroup of G. Then X, the homogeneous space G mod K, which I denote by X, will be called a rank 1 symmetric space of non-compact type. Example, this is SL2 mod SO2. This is really upper half plane, and this is n comma 1 mod SON. This is the real hyperbolic space. Here SO net n comma 1 is really connected component of identity inside SON comma 1. Similarly, complex hyperbolic space SUN comma 1 mod SUN. These are typical example of rank 1 symmetric space of non-compact type. Since this X is equal to G mod K, we can identify continuous functions on X with right K invariant continuous function on G. Similarly, we can identify smooth functions on X with right K invariant smooth functions on G. See, one can show that this X is a really Riemannian manifold and the Riemannian metric is left G invariant. So eventually this distance function will be also left G invariant. Okay, so let rho equals the half sum of positive roots. Rho is a really positive quantity associated to the geometry of the space X. Precisely, rho is the half of the limit of the mean curvature of the geodesic spheres as the radius of the sphere tends to infinity. So now the thing is, since X is a Riemannian manifold, so we can fix a base point and we can declare that point as origin, and so we can talk about radial function. So as you know that we can identify always radial function on a matrix space with a function on non-negative real. Here also we will do that. So here actually, since X is equal to G mod K, I will fix the identity coset as my base point. Okay, so it is known that for lambda, okay, so this is definition. For lambda belongs to C, let phi lambda be the unique radial function on X with respect to the origin O is equal to EK, satisfying delta phi lambda is equal to minus lambda square plus rho square, and phi lambda O is equal to 1. So precisely what it says, for each lambda belongs to C, there exists a unique radial eigenfunction of Laplace Beltrami delta with eigenvalue minus lambda square plus rho square, and which assumes the value 1 at the point origin. Known that phi lambda is equal to phi of minus lambda and phi of I rho is equal to phi of minus I rho is equal to 1. If lambda is equal to plus minus I rho, then lambda square plus rho square is equal to 0. This will correspond to a harmonic case. So it says that constant function 1 is the unique radial harmonic function on X, which assumes the value 1 at the point origin. Okay, these phi lambdas are really basic building blocks of eigenfunction of delta. These are called elementary spherical function. So as I told you that in any Riemannian manifold, we can talk about Riemannian measure and we can integrate functions on it. We can integrate function on it. Therefore, I define this psi lambda is really 1 by a measure of B O comma R into integration of over B O comma R phi lambda X dx. Here dx is the Riemannian measure. So since phi lambda is equal to phi of minus lambda and phi of I rho is equal to phi of minus I rho, so this will give you psi lambda is equal to psi of minus lambda and psi of I rho is equal to psi of minus I rho is equal to 1. Phi lambda is a strictly positive radial function for lambda belongs to imaginary line. I have written that. We will use that thing. Okay, this thing. Okay, this thing I have written. So of phi lambda x is less than equal to phi of imaginary part of lambda x for each x belongs to x. Imaginary part of lambda less than 0 and r greater than 0, we have this limit r tends to infinity e to the power minus imaginary part of lambda minus rho r into phi lambda r is c lambda, where c lambda is the Harish-Chandra C function. Remember, this phi lambda is a function on x, but since really phi lambda is a radial function, we are writing phi lambda r. We are treating phi lambda as if it is a function on non-negative reals. Okay, so I will refer this equation 1 as a Harish-Chandra estimate, and I will use this equation on later. Okay, so it is known that the function c lambda has neither 0 nor pore in the region imaginary part of lambda less than 0. Let lambda not belongs to R. Let lambda is not in non-zero. Sorry, let lambda not belongs to R be fixed. owing to the fact that phi lambda is equal to phi of minus lambda, and to equation we can easily get that there exists r lambda greater than 0, so that mod of phi lambda r is comparable to e to the power mod of imaginary part of lambda minus rho r for all r greater than r lambda. Now, similarly, I have phi naught r is comparable to 1 plus r e to the power minus rho r for all r. Now let lambda belongs to C with mod of imaginary part of lambda less than. If we use this estimate, this phi naught r is comparable to 1 plus r into e to the power minus rho r, and mod of phi lambda r is comparable to e to the power mod of imaginary part of lambda minus rho r, and mod of phi lambda x is less than equal to phi of imaginary part of lambda x. If you use these three things, one can show that limit r tends to infinity, phi lambda r is equal to 0. So what I am saying that limit r tends to infinity, phi lambda r is equal to 0 for all lambda belongs to C with mod of imaginary part lambda, mod of imaginary part of lambda less than 0.
Sorry, can I ask a question?
Yeah, yeah.
What is this Harish-Chandra C function? What is it? What is the context?
So this is some.
I understand that can be a definition, but what?
Actually, there is some definition, but I don't want to go into it now.
No, I understand. I mean, I'm saying, I'm just asking for curiosity. What is the importance of that function?
Actually, it is very important function, but okay, can I answer?
In what context?
See, the thing is, if you have this equation, you can get that estimate, right? Mod of phi lambda.
Yes.
And these estimates are useful in analysis. So if you want to do harmonic analysis, then you have to do these things. And okay, if so, and we will see that how it is useful. I will illustrate with one example at least. So generalized mean value property. Let f be a continuous function on x. Then if it says that f is an eigenfunction of delta with eigenvalue minus lambda square plus rho square, if and only if this MRF is equal to phi lambda RF for all r greater than 0. So similarly, there is a generalized volume mean value property which says that f is an eigenfunction of delta with eigenvalue minus lambda square plus rho square, if and only VRF is equal to psi lambda RF for all r greater than 0. Now, in view of, remember, we have to generalize this so-called weights result. So in view of this generalized spherical mean value property, one would like to ask this following question. Let f be a continuous function on x so that limit r tends to infinity, MRF minus phi lambda RF is equal to 0 uniformly on compared subset of x. Will it imply that f is an eigenfunction of delta with eigenvalue minus lambda square plus rho square? Now, the thing is, if lambda is equal to plus minus I rho, this phi lambda r is equal to 1. I have told you that this result is true, but for any general lambda, this result is not true. Answer is no in general.
So before you ask this question for Euclidean space, this is not.
Actually, I have actually after completing this work, I really saw in the Euclidean thing it is not known, so I wrote for Euclidean. Okay, so answer.
Euclidean case also similar result.
Yeah. Yeah. So answer is no in general.
But if Benjamin divide is only for the
Harmonic.
They don't use any property of the Bessel function.
No, it is not actually needed actually. Because the function is itself one, right? So what they will use. Okay. So answer is no in general. Let us quickly really go through the example. Recall that if mod of imaginary part of mu is less than rho, then limit r tends to infinity phi mu r is equal to 0. I fix lambda belongs to C with mod of imaginary part of lambda less than rho. Let mu belong to C, we saw that mu is not equal to cos minus lambda and mod of imaginary part of mu is less than rho. Let fx is equal to phi mu x. See, phi mu is an eigenfunction of delta with eigenvalue minus mu square plus rho square. Now the thing is, therefore, from generalized spherical mean value property, you will get MRFX is equal to MR phi mu x. This is equal to phi mu r into phi mu x. PT mod of MRF minus phi lambda RF. This is equal to limit r tends to infinity. If you put the MRF is equal to phi mu r in phi mu and f is equal to phi mu, you will get limit r tends to infinity mod of phi mu r minus phi lambda r into phi mu. But since mod of imaginary part of mu is less than rho and mod of lambda is less than rho, therefore this will go to 0 uniformly on compact subsets of X. Clearly, delta f is not equal to minus lambda square plus rho square f, because delta f is equal to minus mu square plus rho square f. But the thing is, we have taken that mu is not equal to plus minus lambda. Now the thing is, okay. So it says that if you want to generalize the weights result for eigenfunctions of Laplace Beltrami operator, we need to pose our question in a different way. So this is generalized spherical mean value property. It says that delta f is minus lambda square plus rho square f. If and only if this MRF is equal to phi lambda rf for all r greater than 0. So hence, if delta f is equal to minus lambda square plus rho square f and phi lambda r not equal to 0, then I will get MRF divided by phi lambda r is equal to f. So I will use this equation which I have written in blue line, MRF by phi lambda r is equal to f, to pose my question. So question is, let it be a continuous function on x, so the limit r tends to infinity 1 by phi lambda r MRF x is equal to fx for every x belongs to x, uniformly on compact subset of x. As r tends to infinity on the set r greater than 0, so that phi lambda r not equal to 0, will that imply that f is an eigenfunction of delta with eigenvalue minus lambda square plus rho square. Now observe, since phi lambda occurs in the denominator, I have to take r tends to infinity by avoiding zero sets of the function are going to phi lambda r. That is, I have to take limit r tends to infinity on the set r greater than 0, so that phi lambda r not equal to 0. So answer to, so this question is positive. So now I will state the main result of my talk. And the thing is, actually, we will state a little more general result than this. So let us see. Let f and g be two continuous functions on x. If for a fixed lambda belongs to C, 1 by phi lambda r, MRFX converges to gx for every x belongs to x, uniformly on compact sets. Then as r tends to infinity on the set r greater than 0, so that phi lambda r not equal to 0, then g is an eigenfunction of delta with eigenvalue minus lambda square plus rho square. Now observe, okay, so look at the statement very carefully. So let me read this once more. Let f and g be two continuous functions on x. If for a fixed lambda belongs to C, 1 by phi lambda r, MRFS converges to gx for every x belongs to x, uniformly on compact sets as r tends to infinity on the set r greater than 0, so that phi lambda r not equal to 0, then g is an eigenfunction of delta with eigenvalue minus lambda square plus rho square. Observe, in Weights result, there is only a single function f, but here we are taking two different functions f and g. In Weights result, g is equal to f. Since we are taking two different functions, our result is really much more general than Weights result. Now, as I have said, that since phi lambda r occurs in the denominator, I have to take r tends to infinity by avoiding the zero set of the function r going to phi lambda r. Now, since this phi lambda r occurs in the denominator, we would also like to know about the zeros of the function r going to phi lambda r. It turns out that if lambda belongs to imaginary line, this phi lambda r is positive. Okay, so I have written that if lambda belongs to imaginary line, this phi lambda r is a positive function. For that case, if lambda belongs to imaginary line, we don't have to bother how we will approach r towards infinity. So in principle, if lambda belongs to imaginary line, you can remove the red part of this theorem. Now, if lambda not belongs to R, then I have told you that mod of phi lambda R is comparable to e to the power mod of imaginary part of lambda minus rho R for all large R. But since we are taking R tends to infinity, in that case also we don't have to bother. Okay. Now, if you combine those two things, we have really covered the case when lambda is not a non-zero real number. So let us see what I have. Okay. So for
this one, you can call it the modified mean value property, or the averages. MRF divided by phi lambda r. Lambda is I rho that.
yeah, in this
Set of,
yeah, that is the thing.
seems to be the right one.
Yeah,
In this case.
yeah. For that reason, I am calling this limiting mean value.
So could you just go back to the previous slide for a moment? thing.
So instead of F, I have taken G. This is a little more general.
Okay. Yes. So of course, so in other words, the thought process is, do I have an asymptotic mean value property?
Yeah.
But then, out of curiosity, is it that in establishing that this is yes, you were able, that is the stuff in red, you were in fact able to prove a more general result?
Little more
Or
general.
are they very different pieces of thinking that comes? In other words, in answering your question in the affirmative, is it the same kind of analysis that gives you a more general result, or you have to do something very different?
Okay, so the thing is, okay, so when you do actually, okay. So the thing is, if lambda belongs to imaginary okay, lambda is equal to I rho, this is the harmonic. If lambda belongs to imaginary line, this phi lambda is positive. In those cases, actually we don't have much problem. Okay, but when lambda is a non-zero real number, we have to deal with zero sets of this phi lambda. We have to go inside Jacobi analysis. Then this problem becomes. That is the question.
G is already an eigenfunction with eigenvalue lambda squared plus some squared. That property is satisfied because all those guys are going to be constants, right? So it's sort of perturbing G and then add something. That something goes to zero, then you get the same.
Yeah.
So there is some room.
So yeah, it says that whatever the non-eigenfunction part, it
that goes to
zero in the limiting process. Okay, I will tell you. Okay, so hence for lambda not belongs to R star, this set is F bounded, so we don't have any problem. The real problem is when F is unbounded, and that happens for lambda belongs to R star. This can be proved using something Jacobi analysis. And but for this example, XL2 mod SU2, this is hyperbolic three space. This is phi lambda R is equal to sine 2 lambda R by lambda sine S2R. Since this phi lambda R is given in terms of sine function, you can clearly see that F is unbounded. Now, second thing is one cannot replace the continuous limit by any arbitrary sequence Rn with limit n tends to infinity, Rn is equal to infinity. So let us give this counter example. Okay. We'll fix lambda belongs to C with so remember this thing. What I am showing that one cannot replace the continuous limit by any arbitrary sequence. Okay, Rn. So I am giving the counter.
Yeah, it will be just be discrete. Bounded or unbounded, it's going to be discrete. Then always about.
So what about?
Lambda.
That is discrete. But what I am asking that last question is clear. I cannot replace the continuous limit by any arbitrary sequence Rn with limit n tends to infinity Rn is equal to. Okay, fix lambda belongs to C with imaginary part of lambda less than 0. We fix mu belongs to C with lambda not equal to mu, and imaginary part of lambda is equal to imaginary part of mu, and real part of lambda less than real part of mu. So let Rk is equal to 2k pi by mu minus lambda, k belongs to n. Now, since imaginary part of lambda is equal to imaginary part of mu, this Rk is a real number, but real part of lambda less than real part of mu, this 2k pi by, therefore this Rk is a positive real number. Now it is clear that limit k tends to infinity, Rk is equal to infinity. Now I look at this thing, limit k tends to infinity, pi mu Rk divided by phi lambda Rk. Now this is equal to, so I do a multiplication and division. So this is called limit k tends to infinity, e to the power minus I lambda minus rho Rk divided by e to the power minus I mu minus rho Rk, and I divide that thing. So we will get this e to the power minus I mu minus rho Rk into phi mu Rk divided by e to the power minus I lambda minus rho Rk into phi lambda Rk. So then I can separate out these two things, and I am doing the I will do some simplification. This is the first part. The limit k tends to infinity, e to the power I mu minus lambda into Rk. The limit k is, second part is limit k tends to infinity, e to the power minus I mu minus rho Rk, phi mu Rk divided by e to the power minus I lambda minus rho Rk into phi lambda Rk. Now I put Rk is equal to k pi by mu minus lambda. Then the first part will be limit k will be limit k tends to infinity e to the power I to k pi. So this is equal to 1. So the first part will contribute to only 1. And in the second part, I will push the limit to the numerator and denominator. And now that will be limit k tends to infinity e to the power minus I mu minus rho r k by into pi mu r k divided by limit k tends to infinity into e to the power minus I lambda minus rho r k by pi lambda into pi lambda r k. But remember this thing, imaginary part of lambda less than 0 and imaginary part of mu less than 0. Now I use the Harish-Chandra estimate, which I told you. So that will be this is equal to C mu by C lambda. And since I am taking this imaginary part of lambda less than 0 and mod of imaginary part of mu is equal to imaginary part of lambda, therefore imaginary part of mu is less than 0. And in imaginary part of lambda less than 0, this C lambda has neither 0 or not 4. So this constant cannot be 0 or this constant cannot be 0. Okay. So what I am getting, limit k tends to infinity pi mu r k divided by pi lambda r k is a constant which is not equal to 0. Okay. So now at fx is equal to pi mu x and gx is some constant time fx. Okay. This constant c times fx. Now mrk fx is equal to mrk into pi mu x. So this is equal to pi mu rk into pi mu x. Okay. So therefore this is equal to pi mu rk into fx. Okay. So hence we get limit k tends to infinity 1 by pi lambda rk into mrk fx is equal to limit k tends to infinity pi mu rk divided by pi lambda rk into fx. This is the constant. So we know that limit k tends to infinity pi mu rk divided by pi lambda rk is some constant c. So that is cfx and this is gx. So and this convergence is uniform on compact subsets of x. Clearly delta g not equal to minus lambda square plus rho square g, because delta g is equal to minus mu square plus rho square g, and we have taken lambda not equal to plus minus mu. So okay, so we cannot replace the continuous limit by any arbitrary sequence. So now this is the result I have described for sphere average. Analogous results holds true for ball average as well. So let us state that result. Let f and g be two continuous function on x. If for a fixed lambda belongs to C, BRFX divided by psi lambda r, this converges to Gx. For every x belongs to x, uniformly uncompact sets as r tends to infinity on the set r greater than 0, so that psi lambda are not equal to 0. Then G is an eigenfunction of delta with eigenvalue minus lambda square plus rho square. Now it turns out that when one solves this problem is much difficult than this ball of sphere average thing. And as Euclidean analysts have pointed out, that this if lambda is equal to I rho, this ball average thing will give a proof from the ball average theorem. You can deduce the sphere average theorem. Okay, and that is also true if lambda is equal to IR, because if lambda belongs to imaginary line, this we will use this fact that this psi lambda and phi lambda are positive functions. What is psi lambda? This is actually I define. This is for a transform of the ball actually sphere. So this is the thing.
Integral of the spherical function over.
Yeah. So there is some normalization, but that is it. So the thing is, okay, so this problem is much difficult than sphere average case. And if to solve this problem, one need to understand these Jacobi functions. So in the sphere average case, one can avoid that Jacobi analysis. One can use Harish-Chandra series for that. Okay, so this is the result for ball average thing. Similarly, we have also proved an analogous result for cell average. And okay, and in this ball average case, one can have all exactly the similar remarks which I have discussed for the sphere average case. Here also one cannot replace the continuous limit. One cannot replace the continuous limit by any arbitrary sequence. So the thing is, okay, observe in these theorems, actually this question makes sense for pointwise convergence also. We have assumed only uniform convergence on compact sets. And the thing is, we have not done anything for pointwise convergence. And another thing you observe that we have not taken any growth condition on the function f and g. We have just simply assume that the function f and g are continuous. So the natural question arises here: what happens if you assume some growth condition on the function f and g? So suppose you assume some growth condition on the function f and g. So can you get better results, or can you give easier or different proofs? That is the question. It turns out that if you assume some growth condition on f and g, so you can prove some better results, and you can also give easier proofs, or maybe, or in some cases you can give completely different proof. So let me state one result for which involve let me state one result where I assume certain growth condition on f and g. So for 1 less than equal to p less than infinity, we define the weak LP space by LP comma infinity to x is the collection of all measurable functions from x to c, so that supremum alpha greater than 0, supremum over alpha greater than 0, alpha df alpha to the power 1 by p less than infinity. Here df is the distribution function of f, where df alpha is the measure of the set x, so that mod of fx greater than alpha. Now this is my result. Fix a lambda belongs to imaginary line. Let f and g be measurable functions on x, so that f satisfies one of these three conditions. Condition is mod of fx is less than or equal to some constant times phi lambda x for almost every x belongs to x. And second condition is f is a weak LP function for some p belonging to open interval 2 comma infinity, satisfying mod of lambda is equal to 1 minus 2 pi p rho. And third is f is a bounded function and lambda mod lambda is equal to rho. So we have this condition on the function f. Now if limit r tends to infinity, 1 by psi lambda brfx is equal to gx for almost every x belongs to x, then g is an eigenfunction of delta with eigenvalue minus lambda square plus 2 square. Observe, here actually we are getting a better result because we are assuming that almost everywhere convergence on the function. Now the thing is, and another thing to observe, that I have taken lambda belongs to imaginary line. So for lambda belongs to imaginary line, as I have told you, that phi lambda is a positive function. So consequently, this psi lambda is also a positive function. For that reason, that so in the proof actually we have used this property that psi lambda is a positive function. Now these are some results which I wanted to state for the purpose of my talk. The rest part of the talk will be devoted to give a proof of weights result in the Euclidean setup. Okay, since I will discuss only Euclidean thing, so I hope you will be able to understand. So precisely this is the result by Benjamin Weight. If for a continuous function f on Rn, limit r tends to infinity, brfx is equal to fx, uniformly uncombat sets, then f is a. Yes.
So you have f bounded by phi lambda.
Yeah.
You need phi lambda there or just e to the lambda minus 4?
That is the thing.
That will be.
Okay. The result of by Benjamin Weight. If for a continuous function f on Rn, limit r tends to infinity, this brfx is equal to fx uniformly compared sets, then f is a harmonic function. We will prove a slightly general result. So let f be a continuous function on Rn, so that limit r tends to infinity, brfx is equal to gx uniformly over compared subsets of Rn, then g is a harmonic function. And I will remember this notation. I hope this brfx is nothing but h convolution mrx. So you will use this notation now. Okay. So what I will do, I will prove the result first in the radial setup. Then I will extend the result from radial to non-radial setup. So this is I will begin with a lemma. Let f be a radial continuous function on Rn with limit r tends to infinity, f convolution mr0 is equal to 0. Then limit r tends to infinity, f convolution mrx is equal to 0 for every x belongs to Rn. It says that if for a radial continuous function on Rn, if ball average of f at the point 0 goes to 0, then for any x belongs to Rn, this ball average of f will go to 0. So recall that this Br is the notation we have used for volume of B0 comma R, and alpha n is the measure of asymptotic. Now since f is a radial function, a radial continuous function, it will descend to a function on non-negative real, precisely if you will set this g of norm x is equal to fx, this g is well defined. Okay, so g is the corresponding function on non-negative reals. Now this is the expression for f convolution MR0. I simply write the definition 1 by volume of b0 comma r into integration over b0 comma r fy dy. Now I use the polar coordinate. So this is equal to 1 by vr integration over sn minus 1 integration from 0 to 1 f of sw s to the power n minus 1 dx this is w. Now f of sw is really gs by the definition. So I put that. So this is equal to 1 by vr integration over sn minus 1 integration from 0 to r gs s to the power n minus 1 ds into d sigma w. Look at the blue part. This is really independent of w. So I can take that out and and rest of the thing I integrate. So this is equal to alpha n by vr integration from 0 to r gs s to the power n minus 1 ds. Simply I am getting f convolution mr0 is equal to alpha n by vr integration from 0 to r gs s to the power n minus 1 ds. The hypothesis limit r tends to infinity f convolution mr0 is equal to 0. So now the thing is, therefore, from hypothesis, we will get limit r tends to infinity alpha n by vr integration from 0 to r gs s to the power n minus 1 ds is equal to 0. Now fix x belongs to Rn, and for this fixed x, I will prove the limit r tends to infinity f convolution mrx is equal to 0. Now for this fixed x belongs to Rn, we can obtain a constant cx greater than 0 independent of r, so that b mod of br plus norm x by vr less than cx for any r greater than norm x. This can be easily proved because br is some constant time r to the power n. So you put the definition of br plus br. So you put that thing there and take limit r tends to infinity. You can easily get this constant. Okay. So what fixed? Okay. So now from this equation 2, what I will let epsilon greater than 0 from this. Let epsilon greater than 0 be given. From this equation 2, I can obtain an m greater than 0 so that mod of 1 by vs integration from 0 to s gt t to the power n minus 1 dt is less than epsilon by alpha n cx whenever s is greater than m. So remember these two estimates. Okay, we will use this thing later. So first estimate says that for this fixed x belongs to Rn, if r is greater than norm x, this mod of vr plus norm x by vr, this is bounded by cx. And second thing is says that if s is greater than m, 1 by vs integration from 0 to s gt t to the power n minus 1 dt is less than epsilon by alpha n cx. Okay. For r greater than norm x, we have this thing mod of f convolution mrx is equal to simply I write the definition. This is really mod of 1 by volume of bx comma r into integration over rn fy chi d0 comma r x minus y dy. Now I use the polar coordinate. This is equal to simply 1 by vr. Now integration over sn minus 1 and integration over r plus f of tw chi b0 r x minus tw t to the power n minus 1 dt d sigma w. Now, okay. So now pay some attention here. So this chi b0r x minus tw is 0 if and only this norm of x minus tw greater than equal to r. Okay. Now just concentrate on the second expression. You fix this w. Yeah. So what is the problem? Greater than equal to r. Did I say less than equal to r?
Oh yeah, 0.
Okay. Okay. So I fixed w belongs to sn minus 1, and so now this is the picture of bx comma r. This is ball of radius r with center at x. Okay. Now since I am taking r greater than norm x, so 0 will be there. Now if we fix w belongs to sn1, sn minus 1, if I look at the ray s going to sw, where s is greater than 0, so this will be something like this. Okay. Now any point here can be represented as tw. So this distance is really, so this vector is really not x minus t w. So, so if this distance is really greater than r, greater than equal to r, this is 0. Okay. Now, the thing is, let us call this point is really rw. Okay. So this distance is really rw. Okay. Now observe that x minus tw naught is equal to r if and only if t is equal to really rw. If t is equal to rw, this is this point, and the x minus tw naught will be really r. Okay, and if t is really greater than rw, this x minus tw naught, this will be really greater than r. So if t is greater than rw, so this will go outside. This x minus tw naught will be greater than r. So for the second thing, for the second integral, I have to integrate from 0 to rw. Is this clear? If t is greater than rw, then x minus tw norm is greater than r. Therefore, it will be 0. So I have to only integrate from 0 to rw. So for each w belongs to Sn1 minus 1, let rw is the value of t for which norm of x minus tw is equal to r. So this is my picture. This is my x. This is my o. This is my line s going to sw. Any point is tw. So this is my x minus tw. This is rw. This is r and x. So okay. Now this distance is really rw. Okay. So I am writing the distance here. And this distance is norm x. And this distance is r because this is radius. So from triangle inequality, we will get this. We will get this thing that rw is less than equal to this r plus norm x and greater than this r. From triangle inequality, we will get r minus norm x less than equal to rw less than equal to r plus norm x. So from previous figure, we get this thing. Hence, if r greater than m plus norm x, then rw is greater than equal to r minus norm x, and r is greater than m plus norm x minus x. This is equal to m. So hence, if for r greater than m plus norm x, mod of f convolution mrx, this is equal to the same thing which I have written in the previous case. This is equal to 1 by vr integration over Sn minus 1, integration from 0 to rw gt to the power n minus 1 dt d sigma w. Now I will do a multiplication and division. So this is equal to integration mod of integration over Sn minus 1 vrw by vr into 1 by vrw integration from 0 to rw gt to the power n minus 1 dt d sigma w. Now I will put the mod inside. So the equality will be less than equal to, this is equal to mod of vrw by vr into mod of 1 by vrw integration from 0 to rw gt to the power n minus 1 dt d sigma w. Now the thing is, since rw is less than equal to r plus norm x, this vrw is less than r plus norm x. So I can bound the first quantity which I have written in blue. So this is less than equal to the first quantity I can bound by mod of r plus norm x by vr, and I will keep the second quantity as it is. Okay. Now, if you remember that I have told you in the beginning that this blue quantity is really dominated by some constant Cx. Okay. And since this Rw is greater than n, this red quantities will be dominated by epsilon, alpha, and Cx. Okay. And this is a d sigma w. So where I like, okay. Okay. Actually, I have told you this is less than Cx, and okay. I am using these to estimate. Okay. So if the Cx will cancel out, and if I will integrate everything, so this will be epsilon. Since epsilon is arbitrary, I will get limit at infinity f convolution mrx is equal to 0. Now, now I will prove another lemma. Let f be a radial continuous function on Rn with limit r tends to infinitive f convolution mr0 is equal to n. Then limit r tends to infinitive f convolution mrx is equal to n for every x belongs to Rn. The previous lemma is a special case of this lemma where you put L is equal to 0. It says that if all average of A at the point 0 converges to L, then for any other point X, it will converge to L. Precisely, this is Watt's result for a radial continuous function. See, in case of harmonic, we know that in case of Rn, any radial continuous, any radial harmonic function is a really constant function. So because this is what we are getting, because the limit function is constant here. Okay. So let gy is equal to phi minus L. Then g is a radial continuous function on Rn with g convolution mr is equal to f convolution mr minus L. So hence limit r tends to infinity f convolution mry is equal to L if and only if limit r tends to infinity g convolution mry is equal to 0. Now since limit r tends to infinity f convolution mr0 is equal to L, therefore limit r tends to infinity g convolution mr0 is equal to 0. Now g is a radial function and I can previous lemma to the radial function g. Applying the previous lemma to the radial function g, we will get that limit r tends to infinity g convolution mrx is equal to 0 for every x belongs to Rn. Now look at the blue line. From the blue line, you will get that limit r tends to infinity f convolution mrx is equal to L for every x belongs to Rn. Okay, so this finishes the proof for radial thing. Now the thing is, recall this is the definition of Rn. We have two observations. Let hi I belongs to n be a sequence of continuous function on Rn converging uniformly to H over compact sets. Okay. Then for x belongs to Rn, this Lx hi will converge to Lsh as I tends to infinity uniformly over compact sets. Okay. This is clear because translate of a compact set is compact. Since this S0 norm x is compact and Rf is nothing but this average of f over sphere of S0 norm x. So this using dominated convergence theorem, one can easily prove that R of radial part of Hi will converge to radial part of H pointwise as I tends to infinity. So remember these two observations. So first observation is if for any fixed x belong to Rn, Lxhi will converge to Lsh as I tends to infinity uniformly over compact sets, and radial part of Hi will converge to radial part of H pointwise as I tends to. Now this is our theorem which I want to prove. Let f be a continuous function on Rn so that limit r tends to infinity f convolution mrx is equal to gx uniformly over compact set of Rn, then g is harmonic. Fix x belongs to Rn. By the hypothesis and observation A, which I have told you before, we have this Lx f convolution mr will converge to Lxc uniformly on compact sets as r tends to infinity. Now I will take the radialization operator. By observation B, we get radial part of Lx f convolution mr converge to radial part of Lxc pointwise as r tends to infinity. Since radial part of Lx f convolution mr is nothing but radial part of Lx f convolution mr, so what we will get this radial part of Lx f convolution mr will converge to radial part of Lxc pointwise as r tends to infinity. So this thing I will write in the next line. Thus for all y belongs to Rn, we have limit r tends to infinity radial part of Lxf convolution mry is equal to radial part of Lxcy. Okay. So in particular, if I will put y is equal to 0, then that will give you limit r tends to infinity r of Lxf convolution mr0. This is radial part of Lxg0, and this radial part of Lxg0 is nothing but gx. Okay. Now this radial part of Lxf is a radial function, so I can use that previous lemma. Okay. So from that previous lemma, I will get this thing, and so applying the previous lemma to the radial function r Lxf, we get limit r tends to infinity r of Lxf convolution mry is equal to gx. Now look at the equation 3 and 4. So owing to 3 and 4, we will get radial part of Lxgy is equal to gx for all y belongs to Rn. But since x is arbitrary, so you can see that this equation r of Lx is gy is equal to Gx for all x belongs to Rn and for all y belongs to Rn. This is nothing but actually, if you remember, in the beginning, I told you that this equation says that G satisfies the spherical mean value property. So R of Lx Gy is equal to Gx for all x belongs to Rn for all y belong to Rn. That means G satisfies the spherical mean value property, then G is harmonic then. Okay. So if in case you do not remember that, so this is the thing. Since m of norm y Gx is equal to R of Lx Gy, we have this m of norm of y Gx is equal to Gx for all x comma y belong to Rn. Therefore, G is hard. So I have discussed the mean value asymptotic mean value property when radius tends to infinity, and I have proved this result for Euclidean set in for harmonic case. Now one can ask a similar analogous question that what happens when our radius r tends to 0. So when the radius r tends to 0, so we are in a local setup and any manifold is locally Euclidean. So using the result of Rn, so one can have an analogous result, but that result is not difficult because results of Rn will give that result. But that result is really interesting and also useful. So this is the thing. This is the Euclidean result due to Basque. If f is a continuous function on an open set D of Rn, then f is harmonic on D if and only limit r tends to 0, mrfx minus fx by r square is equal to 0, uniformly on compact subset of D. Okay, so now, so this is our result. If a continuous function f on x satisfies limit r tends to 0 plus mrfx minus phi lambda rfx by r square is equal to 0 uniformly on compact subset of x, then f is an eigenfunction of delta with eigenvalue minus lambda square plus 2 square. Now these are the results which I wanted to talk. So I will finish with one more slide. So our research plans and ongoing works to prove fitting mean value property for cell average. I have told you that we have proved some result for cell average where we have assumed that the width of the cells lie in between some constant number AB. Okay. So if D is the width of that cell, so we have taken only those cells where this width of that cells will lie in between some constant number A and B, where A and B is fixed. But we have not done anything for limiting mean value property where for cells of fixed width. So okay, so we want to do that and to generalize above results to higher than.
What if we don't take limit? Just achieve mean value test by cell average.
We have all cell average. I mean, see, the thing is cells have some width, right? So that width should be lying in between this.
Where is it? Rn or?
Symmetric space, dimension space in fact. So to generalize above results to high rank symmetric spaces and other Riemannian manifolds where the above question makes sense. We have already started working on it and we have got some results also, but we have not completed it fully. So the thing is, another thing to prove limiting mean value property under pointwise convergence for a continuous function f instead of uniform convergence on compact set. And this is the thing to assume some growth condition on the function and prove better results. And with this, I would like to stop, and these are my reference. And thank you for your attention. I will be happy to answer your questions. Euclidean proof actually Wells proof of Wade's proof, right? You mean this is now this he has taken the second same function here, but actually we have ramified each proof.
Is not used in the rank points in the space.
No, yeah, see the result which I am showing, we will not really see much difference with that of rank one symmetric spaces. But that doesn't mean that you can straight away put the result and prove the result like that. But the thing is, there are some obstructions which you have to really clear out. very out and we can do it. There are some properties will not be true. For instance, getting that RW, because I have really drawn the figure, and in this case, this is very simple. We can get that RW quickly. But in this rank one symmetric space of non-compact type, we have to use some special property restrictions. That is a really, so in fact, this rank one symmetric space of non-compact type, these are really something called characterization. In fact, all symmetric spaces of non-compact type, where what property you are using is something like this. Yeah. Okay. Something like this, you look at a geodesic, t going to really exponential of tx. So geodesic, this is emanating from set point t in the merit. Now you fix a point. So this is my geodesic, and you fix something point p here, origin say over here, and you look at this thing distance do. Call this function is really gamma. Okay, so what happens in rank one symmetric spaces of non-compact type or dynamic recess space? This gamma is a convex function that you have to use. Okay.
So this is a convex.
So this is a convex function.
So that's also probably true.
Rank one thing actually, yeah. Actually, the thing is, rank one thing is also not necessary, because I told you that we are really generalizing this this Weights result for all eigenfunctions. This I lambda is really the Jacobi function. In the rank one case, these are really explicit cases. So we can use the estimates. The Jacobi analysis is available in the literature. But in the higher rank thing, these are really quite complicated objects. They are called see what is this Heitman of the hypergeometric function. Okay, so and we could not understand those things. For that reason, we are really into that. But this property is also true for all symmetric spaces of non-compact.
You can prove the asymptotic of those functions when you have the same number.
So we could not really get the asymptotics of this thing. I would not really understand much about this. For that reason, we could.
Probably you have to consider more than one.
Yeah. All G managing. Yeah.
So just out of curiosity, this is very mildly related to your talk. I know that you are using intrinsic properties of symmetric space, real symmetric space.
Yes.
But, the only kind of symmetric spaces of non-compact type that I'm familiar with are the Hermitian symmetric spaces of non-compact type. And in the rank one case, these are just the balls. So just out of curiosity, is it easy to describe a classification up to isometry of all real rank one symmetric spaces of non-compact type? I know that your proof is not case by case, it's using properties of symmetric spaces, but I'm just curious, what is the classification up to isometry for such spaces? Is it easy to give?
Up to isometry, I don't know. Cannot give very much satisfaction.
Because in the complex case, it's so easy because it's just.
Oh,
Irreducible one.
classified, but
Yeah,
I do not know.
I mean, that's kind of understood, that when I'm saying classified, it's sort of understood it's the irreducible ones. But there must be a finite classification.
Yeah.
Or a classification given in terms of discrete parameter.
And the exceptional.
And then you have these opinion.
No, he is not asking that. Are you asking that?
Only rank. Only rank. Yeah. So are there sporadic cases even in rank one in the real case? Oh, so these optonionic things show up even in rank one. So
Yes.
No, not optonic. Optonic are not even associated. We want some specific, big quaternion. They don't have, those are cloners.
Actually, so but he's saying that all these results can be proved for even soluble extensions of it's like
Yeah, no, no, I know. That's what I said. I'm only asking out of curiosity because I've attended a lot of talks of this kind, and it seems like the methods use a lot of intrinsic properties because these are all quotients, and we are sort of using this in a very major way. And because in the Hermitian case, I know the answer so well, I was just curious if there's an easy answer in the Riemannian case. So in the Riemannian case, it's even for rank 1, the classification is difficult. So,
No, it is done actually.
I know, I think it's done, or at least in principle fully described.
Yeah, it's completely done. Actually, it is completely done actually, but I do not know.
There are some questions in the chat.
oh, online.
There is a question in the chat. Sorry, should your argument also work for manifolds with negative sectional curvature, since you have some convexity of the distance function in that case?
So I do not know actually. I have not. I cannot answer this question now without.
You cannot have estimates for eigenfunctions and so on.
Yeah,
These terms are not.
Very, I mean, you have to have also some artificial conditions, essentially.
So are there any other questions?
About what? More questions?
No, nothing online, nothing else online.
Yes, there are no more questions.